Hello everybody and welcome back. In this video solution, we'll talk about the problem island perimeter. I'm going to dive into two approaches for it, the iterative version as well as the DFS version. Let's start with the problem discussion, and this is a very simple problem in terms of its setup. You're given a 2D binary grid with ones and zeros, where 1 represents the land pieces, which I've marked it in yellow, and 0 represents the water pieces. I've marked those in blue. And you're also given the fact that there is only one single island in this entire grid, and you have to return the perimeter of that particular island. Nothing more to say about it, so let's dive into the observations for the iterative solution. Let's take the case of this simple square over here. Let's assume this is the only land piece in the entire grid. The perimeter of this cell is going to be 4, as I've marked with the yellow boundaries over here. The question really is, what if I add another cell to the right hand side of it? And in this case, we see that the total perimeter increases to 6. 3 for this cell and 3 for this cell. But I'll say, instead of looking at those two cells, let's just keep focusing on this particular cell. So the perimeter earlier was 4, and as we added this another cell to it, the perimeter got decreased to 3. Basically, one of its side got blocked by this other cell over here. And if you realize this much, then I think we can directly jump into the formalization of the logic. So the first thing we want to do when it comes to the iterative logic is we want to iterate over all the cells. Now, if the grid of xy is equal to 0, which means that we're looking at a water body, we can just skip over that point, since that does not contribute anything to the total perimeter. Otherwise, we want to set the current perimeter to be value 4, and we'll start off with the value 4, and we'll see what all its neighbors are. If the right neighbor exists, we're going to do current minus equals to 1. As we saw before, earlier if we had a value of 4, we encountered a right neighbor, we decrease the value by 1. And so this is exactly what we're doing here. As we did for the right neighbor, we're going to do for the left, top and the bottom neighbors as well. Whatever is the remaining is what we'll add to the answer. With this, we can move on to the code for this solution. Let's get started with counting the answer, and we'll return that at the end. Now we'll iterate over all the values. X represents the rows, by the way, and Y represents the columns. And we'll check if grid of x of y is equals to 0, which is the case of water body, then we can just skip over it since it does not contribute anything to the perimeter. Now we'll set the current to be value 4, and we'll say if right neighbor, then do current minus equals to 1. Basically, if the right neighbor exists, reduce the current score by 1 because its side gets blocked by this right neighbor. Now the right neighbor is nothing but grid of x and y plus 1. So we can basically now copy paste this for all the 3 other places. Before we do that though, we need to do a quick sanity check. Y plus 1 may not always be in bounds. Y plus 1 may just go out of the grid, so we'll have to check for that. So only if y plus 1 is less than less than n, which is the number of columns, and this happens, only then you can do current minus equals to 1. Now we can just go ahead and copy paste this and edit it for all of the other 3 values. With this, now we can finally move on to saving this value inside of the answer. So whatever was the current value, we're going to do answer plus equals to the current value. With this, we can do a quick sanity check, and we can submit this. Cool, this works. When it comes to the observations for the DFS solution, not a lot changes. Let's take this case over here. Here we are starting a DFS from this particular cell. Let's zoom in on this and see what happens. When you start a DFS from this point, it is going to go ahead and call all of its neighbors to the top, to the right, left, and the bottom. And earlier in the iterative solution, we were checking the neighbor status if it was water or if it was land or whatever. Instead of doing that, we'll actually go to the neighbor and start a new DFS from that point. Now, depending upon the base conditions, we'll go ahead and return from those DFSs. In fact, part for this solution would look like something like this. So we have this +1 coming over from here. So remember that I started from this point, but it went ahead and called this particular cell. For this particular cell, it looked at itself and said, you know what, I'm a water body, and the earlier cell called me, which probably means that I'm a neighbor of some particular cell, which means that I have to return a count of +1. This logic is applied to all of the water bodies, and so they will get a score of +1 as well. This case is a bit different from the iterative one, and it really shows the differences between DFS and iterative solutions. Because instead of now returning 0 from here, which was the case in iterative solution, we'll actually return +x over here. This x basically represents that what happened if we start a DFS from this particular cell, and so on and so forth as we went for the entire sort of search. And so when we return back from this point, this +x would represent the perimeters for all of this area. And which means that once we have all of these returns, we can just add them and send them back, which we can add and thus return. I think it's time to go and talk about this logic formally, so let's do that. To formalize, we'll say that we're starting from the first land cell. Any land cell works, we just need one land cell. So we'll define DFS of xy. X and y represents the rows and the columns, so exactly where we are inside of the grid. And DFS of xy is just going to return us the total count of that particular cell. So it says, what happens if I start a DFS at the point xy, return me the total count, the total perimeter. Now the base cases are very important in this case, and they need to be handled with care. Going out of bounds or going into water gets us a score of 1. The score of 1 from the water makes a lot of sense, but going out of bounds? Let's actually look at this case over here again. Let's consider what happens if we are at this particular cell. For this particular cell, if I ask you, what is the perimeter going to be? So here it is blocked. Here there's a water body, here there's a water body, and here is out of bounds. If I just wanted the perimeter of this cell, the answer would actually be 3, since only one side of it is actually blocked. The other 3 sides are completely free. Although one of them is still out of bounds, we don't worry about that. So in case we are out of bounds or we are inside of a water body, then we'll return a score of 1. This should make sense now. We'll also say that if we have already visited this particular cell before, we can just return a 0, saying that we don't want to loop around and around and go in an infinite recursion. We'll just return 0 right away. And the generation case for DFS is going to be, we're going to iterate over all the neighbors, so top, bottom, left, right, and we're just going to do count plus equals to DFS of the neighbor. With this, we can finally jump into the code for the DFS solution. Let's go ahead and define the DFS as we saw before, x and y. And we'll say if you went out of bounds, which is not of 0 to x to m, and 0 y of n, if you went out of bounds, or if the current grid cell you're looking at is a water body, in that case, we'll return 1. If the grid cell is, visited is a bit tricky. As I marked before, actually, this visited, I marked it with a star, because if you want to keep track of visited values inside of this entire grid, you'll need another visited grid to take care of it. And so that would increase our space complexity by a lot. Instead of doing that, what we can do is very sneaky. We'll just say, instead of doing this, set the grid of xy to be equals to -1 if it has been visited. So if it has not been visited, so we'll say if grid of xy equals to -1, then which means that it has already been visited. So we can just return 0. And if it has not been visited, we can just set it to -1 and go on with our logic. We'll set the count equals to 0 and we'll do count plus equals to the DFS of x plus 1y. So going to the bottom case, then we'll go to the top case, then we'll go to the right case, and then to the left. At this point, we can safely return the count as the answer for this DFS. The only thing left to do is do the first thing over here. We want to start a DFS from the first land cell. We can do this from literally any starting point. It works for all of those cases, but we can start from the first land cell we encounter. So we'll do for x in range of m, for y in range of m, we'll say return the DFS of xy if the grid of xy is true. With this, we can try submitting this. Cool, we'll do submit. And we see a runtime of 612 milliseconds. Cool. So this is it for the problem island perimeter. Very interesting. And we looked at it from two approaches. First the iterative one and then the DFS one. If you look at it closely, they're pretty much following the same chain of logic. Like we're still iterating over all of those neighbors and we're still figuring out if it's a water body or if it's not, and so on and so forth. Cool. So this is it, and subscribe for more. And as always, thanks for watching.